Hello, this is Brock Lemires, and we are going to be going over the recitation number 4 content in this video, which is on flow control in the programming language C. Many of the images that we'll be looking at were created by Dr. Ross Snyder of the Electrical and Computer Engineering Department here at MSU, so I have his picture and name on here also. So, to start with, the goal of what we're going to do here is we're going to understand the basic flow control in C, and we're going to look at 4 of the most common things that we use to control the flow, which is an if-else statement, a switch case, a while loop, and a for loop. And by the end of this video, you will know what those mean, what those are, and what they mean, and you will also be able to code them up. Okay. Then we're also going to use these looping structures and decisions in order to do some very common tasks that we often encounter in engineering, and that is going to be to use loops to move through arrays. Okay, so we're actually going to have a real application of these concepts in this video. Okay, so up until now, we have written programs that execute a sequence of tasks, and that's fine. Okay, you have to have a sequence of tasks in all programs. But if you think about the way that these programs have been executed, you start off with your libraries, and then you have the int main. We don't even know what that is yet. And then you just have some variable definitions, declarations, and then you do some statements like printf, and you get some fgets, and then you do some, some conversions and assignments. But you just walk through line by line through each of these statements. And then in this example, what we've been doing is we then end the program. So we just go and we're done. Okay, but there are situations where we may want to have the program react to some values. Okay, so what we mean by flow control is we execute the statements in a different way other than just sequentially. Okay, so examples of that might be, you might take this and you might say, you know what I'd rather do than just execute all of them? I might want to execute this sometimes, this set of statements, or in other situations, I might want to execute these statements. So maybe I don't do them every time, I just want to do one or the other. And that gets us into this kind of decision construct, which is selective execution. Okay, so we have statements in our program, but we're not going to execute them all the time. We'll only do it under certain situations. And we also might get into situations where we want to do what's called a loop, or we might want to repeat the execution. You might notice that our programs that we've been writing, they end, but not all programs end. I mean, if you think about your operating system on your computer, it's constantly running, so it's in a continual loop reacting to user input. And so we need a way to actually put our program into a mode where we can repeatedly run loops. Well, we call them loops, but we repeatedly run statements over and over and over. And of course, we can use these together where we are looping and making decisions to start getting a program that's just a little bit more intelligent. Okay, so let's look at the first construct. That's going to be the if-else statement. So this is the syntax for an if-else statement. Okay, there's keywords called if and else, and then you're going to you see this thing that we call the expression. Okay, and here is the way that this works. In the expression part, you are going to have something which is some statement which will be evaluated as either true or false. Okay? And then if this expression is true, you will execute the statement or statements that reside within the curly brackets after the if line. Okay? If this expression turns out to be false, you will not execute this statement. You will instead, or else, execute the statement or statements that reside in the curly brackets after the else statement. So this is the way that we actually start getting to the point where we can do something interesting. Okay? Now here's what's very important. The expression is either true or false. Okay? That is a logic decision. Okay? It is one or the other. So it's very important. You're not going to come in here and say, if 3.14 do this. Okay, what you're going to say is if the value is 3.14. So you think about just that subtle difference of you're always going to put something in this expression that can be evaluated as true or false. Okay, and that's how we do it. Now, another important concept here is that the statements have to exist in your program. So you're going to put a statement that corresponds to if the expression is true, and you're going to put a statement corresponding to if the statement is false, but they exist in the program, and you selectively execute them. Now, there is situations where you could exclude the else statement and just say, I'm only going to print statement 1 or do statement 1 if this is true, and otherwise I won't do anything, and that's fine too, but this is kind of the whole concept of the if-else. Okay, now, expressions that you can use. Okay, first of all, you have a set of expressions or operators that C gives you that will allow you to create logic expressions. Okay, so let's start with the first one, equal to. This is a very common one. You could put within there A is equal to B. Notice that it's two equal signs. That differentiates it from the assignment operator that we've been using before. If you look at this expression, A equal B, it is saying, is A equal to B? The answer to that question is either true or false. Okay, so that is an expression that we could put into our program that will allow us to say either I'm going to do the statement 1 within the curly brackets of the if portion of this if else, or if it's false, I will execute the statement 2 within the curly brackets of the else. Okay, the other ones that you can see is you have not equal to, that's that syntax, greater than, less than, greater than or equal to, less than or equal to. Okay, so these are the expressions, the basic expressions that we use in order to do this. Okay, so let's take a look at a program. Okay, so let's fire up Putty and let's do an example here. So I'm going to go ahead and open up Putty, and I come over here and I'm going to log in, and everything's great. All right, and then why don't I let's go ahead and see where we're at. So I have my directory structures. I do an ls or an ll, and I see that, okay, well, I've got my stuff in here. Let's go ahead and make a directory called rec4, and there it is. Now I'm going to change into rec4, and I'm sitting here. I have an empty directory, and I'm ready to create a program. Let's create a couple different program files for this video, and we'll get used to kind of having multiple files that have different programs in them. I'm going to do Emacs, and let's do one that's called example ex, and then we'll go if, and that'll be a file. Okay, .c. Okay, all right, so here we are. We have this open file, and let's go ahead and get this thing fired up. So we're going to include our standard IO, so we're going to be using the printf and stuff like that, and we don't put that in curly brackets, we put it in these guys. Okay, so now I have my standard IO library. We come down here and we're going to do an int main, no idea what this is yet, and then we open our curly, we close our curly, and while we're down here, let's just go put our return 0. Again, we have no idea what this is. All we do is we write this shell and we're off and running. Okay, so here's what I would like to do. Let's go ahead and do something very simple, such as an if-else statement. Okay, so here's what I'm going to do. I'm going to have just my screen up here, and I'm going to start off by saying let's create some variables. Let's go int a, and we'll set it equal to 5. Okay, so we've created a. Let's go int b is equal to 7. We just created these things. Here is now the syntax for a printf statement. Let's do something where we make a statement that says we're going to print a is greater than b if a is greater than b. And then we'll do a statement that says b is greater than a if b is greater than a. And then what we'll do is we'll come up here and we'll change these integer values, and we'll make and run over and over, and we'll see how it selectively executes. Okay, so we start off. I do keyword if. Notice that it turns into a different color because Emacs recognizes it as a C, keyword. And I'm going to go if a is greater than b, and I close it, open my curlies, and then I'm going to go ahead and close my curly right there. And then I'm going to come over here, and if that expression is true, I'm going to do a print statement that says printf a is greater than b. And then we'll return it, new line, and that's it. So if it's greater, you print that. Okay, this is actually done. I mean, this is a full program right here. It would print this if a is greater than b, and if I don't do anything else, it just won't execute that statement. But what we're going to do is let's go ahead and put an else on here. So I'm going to put an else and then open up a curly bracket, and if that statement is not true, I'm going to do a printf and say, well, b is greater than a. line return. Okay? All right, there it is, and all I got to do is end my curlies, and there I have it. So let's look at this program, and I'm going to do Control X, Control S, and now let's compile this and see if I have any syntax errors. So I'm going to fire up putty again. Here comes putty, and I'm going to go ahead and go boom, load, open, and here is now my compile window. So I log in, and I do a messed up. Okay. And I'm logged in, I do LL, I CD to rec4, and I see my file, okay? I'm going to do a make x example if nothing, and it compiled good, so I lucked out that first time. So let's go ahead and run this thing. So I'm going to go boom, boom, x if, boom. And it says B is greater than A, and that is because that is true. So let's look at what happened here. I put the initial value of A is 5 and B is 7. It came down here and it said, is A greater than B? And the answer for these values was no, it is false. That means it did not execute this statement. It executed the statement within the else portion. So this is great. It worked. Let's go ahead and try changing these. Let's go like A is equal to 8, and I'll save that. And now in this situation, it should execute the first statement. So I come in here, and let's go ahead and make it. Now let's run it. Oh, look at this. A is greater than B. So this is fantastic. I've actually done something that is selectively executing code. Okay, so this is great. Life is good. You might ask yourself, well, what if I wanted to have something a little bit more, involved? What if I have multiple statements that I want to put in there? Well, you know what you do? You just nest additional if-else statements within the else clause, and that's perfectly legal. What you have to do, though, or keep in mind, is it's common coding practice to try to indent these so that you can kind of keep track where the curly brackets are opening and where they're closing, because once you start nesting a whole lot of statements within here, you'll get into this situation where you can't keep track of which curly bracket closes which open curly bracket, and you just run into a whole bunch of compilers. But all you do to add additional logic statements in here is just add in another if clause within the else portion. So let's do an example of that. Notice that this simple example is I have either A is greater than B, and the false portion of it will be A is less than B, except that what happens when they're equal? Okay, so if A is equal to B, we will be printing something that says B is greater than A, because this will evaluate false. So if we want to actually have a statement that says is A greater than B, is A less than B, or is A equal to B, we would need 3 of these. So let's go ahead and let's take a look at how we would do that. So I'm going to go ahead and nest into here another clause. Okay, so here's what I'm going to do. I'm going to come along, and after this else statement, okay, I'm going to go ahead and fire up another if. So the way that I do it is I'm going to come down here and I'm going to create a brand new if. So I'm going to say if, and I'm going to put the statement that B is greater than A. Okay, and I'm going to do that because I will then say, if that's true, I will print B is greater than A. Okay, so that's fine, but that allows me to then say, you know what, if it's not true, so if this statement is not true and this statement is not true, the only remaining thing that could be true is that they're equal to each other, and I can finally put my third statement in here. So what I got to do is I got to be just a little bit careful of my curly brackets. So if you think about it, within this else that I have right here, it's closing right here. Okay, that's the curly bracket that's closing it. This one right here is I have an if, and I've opened up a curly that I can close here, but I want to have an else portion that I'll say open curly, and I want to then do my print statement where I go print F, and I say, you know what, A is equal to B, and then I want to close that curly. Okay, so now I got that little curly right there, and let's see if this looks good. Now, I may have made a mistake in here, so I'll go Control X, Control S, and let's come in here and let's make sure that we can actually compile it. So I make it, it worked, I run it, A is greater than B. Okay, so let's come up here now, and let's now test the second part where I test whether I can tell if B is greater than A. So I change that variable, save it, I go make, run, B is greater than A, so that showed me that this portion of my code works. And now let's test the last one, which is, let me set both of them equal to each other. I save, and now I'm going to come in here and I'm going to do make it, run it, and look at A is equal to B. So I have now written a program that has if-else statements, and I've nested them within each other, and I've gotten familiar with how to use this construct to kind of selectively execute code or statements. Another construct that you can use to selectively execute code as opposed to an if-else is called a switch statement, or often called a case statement. And what happens with an if-else is that if you nest a whole bunch of ifs within else statements, it can kind of become hard to read with all the curly brackets, and trying to keep track of all which ones are open, which ones are closed can become kind of a nuisance, and it'll actually lead to your code not operating as you forget to close certain curly brackets. So another way to do it is using this syntax, and it's more of a tabular way of listing out different options. And what you do is you start with a keyword switch, and then you list in parentheses the variable you're going to check, okay? And then you open the curly brackets, and then for each value that you want to compare it against, you would say case, and then you give the value here, okay? So if it's true, okay, if this variable to be checked is equal to the option, it will execute the statements that you list below the case keyword. To end, or to let the program know when you're done executing statements, because you can have multiple statements, you use the keyword break, okay? And so you just kind of code it up just like this, and you know you're done with the switch statement by closing the curly brackets. And it's a very straightforward and probably in one of the more popular ways to implement a program where you have a lot of different conditions you want to check. So let's do a quick example. So here I'm back in Emacs, and what I'm going to do is Control X, Control Close, and let me show you how to copy a file. So I'm back at my console, and I've got my example ex_if.c. I'm going to make a new file, but I want to copy it from this. So I'm going to do copy, and then what I do is I go exif .c, and that's what the file I'm going to copy. And let's copy it to something called x_switch.c. So if I look at this now, I have copied that file over to xswitch, and now I can launch Emacs on this, and let's see how this goes. Okay, so here I am, and what I'm going to do is come in here, and I copied all this stuff. Didn't really save me much because I'm going to delete all this, but let's do one of these examples where you use a switch statement to do a menu, okay? So let's do the following. Let's have the user enter a number, and then depending on the number they enter, we'll say hello to them in different languages, okay? So let's first create a variable of type integer that's called option, and then let's prompt the user for a number, okay? Now remember, it's going to come in as a character. So what we should do is we should do car, and then we'll do option as a string, and we'll make it 100, okay? And then we'll come down here, and let's first go printf, and then enter 1 for English, 2 for Spanish, and then 3 for French, okay? And then we'll do this, and that now is that. And let's go ahead and let's get a compile under our belt just to make sure we don't have any weird syntax in there. So this time what I'm going to do is I'm going to do make, and then example switch, or excuse me, make example switch, and there's no errors. And then let's go ahead and run example switch, make sure that it's executing. So enter 1 for English, 2 for Spanish, 3 for French, and then it's done, okay? So now we're going to wait for the user to enter something. So I'm going to do fgets, and I'm going to stuff what comes in into my variable called option string, okay? And then the size of it will be size of option, and I'll need to include my library there, so option string. And then I'm going to bring it in from standard input, okay? And then I close that. And then what I want to do is let's convert it. So I'm going to say option gets assigned, and I'm going to convert my ASCII to int and I'm going to convert that string, option underscore string, and now what I'm going to do is I'm going to test this before I do my switch. So I'm going to do printf you entered, and then I'm going to put my information that I just retrieved, line return, and I'll put option here, and let's get a compile under our belt and make sure that this is working. For standard IO, we should be good to go here. So I save that up, I make it, I run it, and I'll say 2, and it says you entered 2. Okay, run it again. 1, you entered 1. Run it again. Don't need to make it. Run it. 3. Okay, so I've got this new program and everything's great. And so now let's go down and put a little switch statement in here. Okay, so I'm going to do this. I'm going to say keyword switch, and I'm going to look at the variable option. Okay, and this is of type int. Okay, so now when I'm ready to go, I go ahead and open this up, and I'll close the curly brackets right here just so that I know that they're closed. And right here, what I'm going to do is I am going to say case, and then I put the option, or the value that I'm going to check against. In this situation, I'm going to check and see if it's 1. Okay, and then if it is 1, I'm going to say printf, and I will say hello. You know, and you always do exclamation point. Okay, and then we'll do a return, and that's it. Okay, now I'm done with my statement, so I do a break and do my semicolon after that, and that's my first case. Okay, and then you know you want to indent these things over. Now here, if option is a 2, so they enter that, I'm going to do printf, and now we're going to say it in Spanish, so we will say hola. And then we will do this, and so that now has handled my second case, and I do a break, and then finally I go case, and I say if it's a 3, you do print f, and now we're going to say hello in French, okay, which is, what is it? Bonjour. All right, and of course exclamation point. All right, now if it's not one of those, this case statement, or after I do my break here, the switch statement will allow me to have a default where if it didn't find that the variable option was equal to 1, 2, or 3, you can do this thing. So I'm going to say, if it wasn't 1, 2, or 3, I'm going to say you didn't enter 1, 2, or 3, and then question mark. Okay, all right. So now we're done with that, and we need a break here. And now the curly brackets for this switch statement are right there, and let's just line everything up so everything looks great. We want to make sure everything looks indented and everything feels so good. Oh, it's so nice. Okay, Control X, Control Save, and let's go ahead and compile this. So I make it, and I have an error. Okay, so let's see. Line 27, what is the issue? It is saying expected a semicolon. Well, I forgot my semicolon after that break. Control X, Control S. Make it. You didn't enter printf. What's it going on here? Oh, forgot a colon there. All right, so this is fun. And let's see, make it again, and we're ready to go. Okay, so now run it. I'm going to enter 1. You entered 1. Hello. All right. Well, run it again. 2. You entered 2. Hola. And then don't need to make it. Run it. Enter 3 this time. Bonjour, huh? And then let's do it one more time, and let's enter 5. It's like, what? And it says you didn't enter 1, 2, or 3. Okay, so this is a very powerful way, and you'll use this one a lot when you program. But this is called the switch statement, and some people just shortcut it as a case statement. But it's a very powerful way to do selective execution of statements. Okay, so now let's look at a different type of flow control, which is a looping structure. So what we've looked at before is how to selectively execute code, but now what we want to do with loops is we want to repeatedly execute code, and we can repeatedly execute code in a number of ways. We can do it forever, or we can have it repeat as long as a condition is true, and that brings us to the first loop that we're going to cover, which is a while loop. Okay, so while is the keyword, and what you do is you you give it an expression. And this is very similar to the if-then statement in that the expression is going to be evaluated as either true or false. Okay, so this can be, a comparison, A is greater than B. It can be when A is equal to B, but it's always going to be evaluated when this expression, or whether it's true or false. If it is true, then the while statement will execute all of the statements in order that are encompassed within this curly brackets, and then it will come back up and it will evaluate the expression again. So you can think about this as, if it's true forever, it will just sit here and loop over and over and over just as fast as it can go. If the expression is ever evaluated false, what it does is it just skips over the statements and then you're done. So that's it. So that's how a while loop works. Now let's take a look at using a while loop to create a counter. Okay, so I have this example of a counter, and what I'll do is let's just code it up. Okay, so again, let's go back into Emacs, and I'm going to do a Control X, Control Close, and now I'm going to go ahead and copy over my last file into another one. So I'm going to go copy x switch.c, and let's make this called x_while.c. Okay, and then let's open up our x_while.c, and here we are. Okay, so now I'm going to go down here, and I'll go ahead and start deleting this. And what we want to do is we're going to make a counter. So as we think through how a counter works, we're going to have a condition that immediately checks whether the counter has reached some preconceived or predetermined value. Okay. Now you're looking at me delete this and you're going, what are you doing here? You've been doing easier to start a new file. That's all right. Okay, so here we go. Let's come in here, and the first thing I'm going to do is let's make a variable called counter, and let's make it kind of descriptively named. So I'm going to have an int counter. So this is going to be a variable called counter, and it's going to hold only whole numbers. And what I'll do is I'll come down here and I'm going to set the initial value of the counter to 0. And let's count from 0 up to 19. Okay, so what we'll do is we are going to make a while loop, and what I'm going to do is I'm going to say I want you to execute everything within these curly brackets that I put right here when counter is less than 20. Now within the curly brackets, what I can do is I can say, as I come through this, what I would like to do is I want to go ahead and do counter equals, or gets assigned, counter plus 1. In this way, every time I come through the while loop, it will increment counter, the variable counter, and so the first time through it'll be counter is 0, it's less than 20, true, so it'll go to 1, come back up into this while loop. It'll say, oh, 1 is still less than 20, so I'll increment it to 2, come back, 2 is less than 20, increment it to 3, 3 is less than 20, increment it to 4, and it will do this until the counter value is incremented to 20, and it will come up here, say 20 is not less than 20, so it will say that expression is false, jump over the last curly bracket, and you're done. Okay. Now, we got to kind of see what's going on, so we can also embed a printf statement in here. So why don't we look at the value of counter as it comes into the while statement before it's incremented? That way, the first time into the counter, you'll actually see count equals 0. So I'm going to go ahead and do a printf, and I'm going to say counter is equal to, and then I'm going to put the decimal value of the integer, which is going to be called I. Not even close, counter. Okay? All right, so I have counter is equal to some value, and then I'm going to insert into there the variable counter, and then I will increment it and then sit in this loop, and it should execute 20 times. Okay? All right, let's Control X, Control Save, and then I come down here, and I'm going to go make example while. No errors, nice. Then I'm going to execute example while. And look at this. 0, 1, 2, 3, all the way up to 19. Okay, now this is something to think about. We always start at 0 and we always count up. So when I said it's less than 20, it will go up to the value 19. What's cool about this is that I could easily come in here and just say, why don't you count up to 99, and look at how quickly I can change the structure of this while, or how many times it executes. So now look at this. I've cranked out just tons of these things, and so it's like, this is a very powerful construct. The last looping construct we'll look at, or looping flow control that we'll look at, is called a for loop. And the for loop kind of came about because a lot of times in program loops, you are going through the loop and you're manipulating a particular variable. And a lot of times you're just incrementing it by 1. So you might come in, like in our counter example, we started at 0. Every time through the loop, we said 1, 2, 3, 4, 5, 6, 7. The reason it's very popular to increment variables by 1 is because you can use them as addresses or indexes to address an array. Okay, so if you remember, you can create an array, which is a one-dimensional vector, and each element within that vector has a unique index. So if you want to look at element 1 within the first element in the array, what you can do is you can say, give me that array with an index of 0, and it'll return that particular element. And we'll get a little more experience with that in a second. But for now, let's look at this for loop, which provides a way to automatically manipulate a particular value or variable, and then what you can do is you can set the initial value of that variable, and then you can also set the maximum value or the end value of the variable, and then you can give it what you want to do to that variable. So like increment it by 1, increment it by a little bit, and it will automatically do this for you. Okay, so here is how the syntax looks. You use a for as the syntax, and you're going to do the first thing you're going to do is you're going to give an initialization of a particular variable. So if you had a counter, it'd say counter equals 0 right here. Then what you're going to do is you're going to give the condition for this loop to stay looping. So typically this is going to be some maximum bound or some minimum bound. So if you set a maximum bound, what you would probably be doing is incrementing up this variable until it reaches a maximum, then you're done. If you set it as a minimum value, then you would start at some maximum initial value and count down. So you put this test in here to make sure that this is when the loop will end. And then you give it the actual thing to do to that variable. So increment it by 1, decrement it by 1, whatever. Okay, so here's an example. Let's do an example of a counter that is exactly like what we did with this while loop. Okay, so let me, instead of starting a new file, actually, let's start it. So let's go Control X, Control Close, and let's go ahead and go copy example while.c to example4.c. And I look at it, and I'm going to go, okay, there it is. So I'm going to go Emacs example4.c, and here we are. Okay, so now what I want to do is I'm going to replace this while loop with a for loop that's going to do essentially the same thing. It is extremely common to have the variable that you're manipulating within the for loop be called I. And that's just what it is. I don't know if it stands for index, but it's very common because it usually is used for an index. Okay, so we'll just start with I to kind of match what everybody usually does. And now here I go. I'm going to type for, and now I'm going to give the initial condition for the variable I'm going to manipulate, which in this situation is I. And so I say I is equal to 0. Then I put a semicolon, and now I give it the test for how long to loop. And I want to say loop as long as I is less than 20. And then every time through the loop, I want to do I is equal to I plus 1. And I write it out. You don't have to. You can do I plus plus if you wanted to increment it by 1, but I always write it out. It's up to you. I open some curlies here, some curly brackets, and this loop is kind of neat because in the while loop I had to actually initialize the variable before I came in. A for loop allows you to initialize it in the for loop definition itself. So as the for loop is entered for the first time, it sets the initial value to I is equal to 0, and then you set what you're going to do each time through, and so it takes care of all the operations for us. All we would have to do if we wanted to see what I was is say printf and then say I is equal to, and then we can print out the value of I by doing it like this. And look at that. That's all I did. I just said I is equal to, and I put the value displayed in decimal of whatever variable is listed here, which is now going to be I. I did a line return. Let's go ahead and save this up. And now let's go over here, and I'm going to do make example4, and no errors. Then I do, let's run example 4. And there you go. That is a for loop. And let's change a couple things. We could have said, let's increment it by 2. Control save. I come over here, make it, run it. Look at, now it incremented by 2. I could also come up here and say, go up to, 100. And so I save it. I come over here, I make it, I run it. Look at how quickly I can change what's happening inside of this for loop. And I don't have to do anything but set up the initial conditions. And it's cool too, because you can also do decrements. So I could come over here and I want to say, I want to count from 13 down to, let's say 0. And each time through the loop, I want to say I equals I minus 1, and I want to loop as long as I is greater than 0, and I could do greater than equal to 0, but let's just check this out. So Control X, Control Save, come over here, make it, run it, and look at, now I'm counting down. So for loops are super powerful, and they become very powerful when you start looking at using the variable you're manipulating as an index to an array, and that's what we'll see next. Now we are ready to actually do something with these constructs. So let's take a look at an example where we're going to use these loops and decisions in order to move through arrays, and how we can use these arrays and our ability now to traverse them to calculate something meaningful. So let's take a look at this circuit right here. So this is called a voltage divider, but it's just a circuit that has a voltage source and it's got 2 resistors. And the things that we might want to calculate for this are going to be the current, and then we might also want to calculate the voltage across R2, which we'll call V out. And if we can calculate the current, you can just use Ohm's law to calculate what V out is. And then if you know the current and the voltage, you can calculate the power. So we could calculate all these different things for this circuit with respect to the R2 resistor. But wouldn't it be nice if we could write a program and have it calculate these quantities for a whole range of values for R2. So instead of just putting it in, calculating them one by one using our program, let's have it in a loop where we calculate for, a variable number. We could have 20 of them, we could have 20,000 calculations. So here's how we're going to do it. We're going to create an array, and we're going to call it R2 array, and it's going to hold a range of values for R2. And what we'll do is we'll set V1 to equal to like 9 volts, we'll set R1 to be 50, and then we'll have R2 sweep from 25 to 75, and we'll be able to adjust how many step sizes are within that range. What we'll do is we'll also have an array called iArray for the current, and it will be the exact same size as R2. And what will happen is that it will hold the corresponding value of the current for each of those values of R2. We'll do the same thing with an array called VOUTArray, and it'll hold the corresponding output voltage for that particular value of R2. And finally, since we have these two, we'll multiply them together and get what we'll call the P2 array, which is the power dissipated in resistor 2. We'll have 4 arrays, and what's neat about it is that they will be the same size, and each location within the array will correspond to the values in the other arrays. So the first value for R2 over in this array will correspond to the first position in I array, and that value will be the current at that first resistor value, and so on and so on. Okay, so let's think about how we're going to do this. First of all, we are now going to get into a position where we're going to be having fixed constants in our program. Things like the minimum value of R2, the maximum value of R2, the number of steps that we're going to have in our array. And we want to start using kind of a global variable or a global constant, so that you'd avoid this whole approach of hard coding values inside of your program where you have the same value used in multiple places, and then you might go back in and change it one area and forget it in someplace else, and it leads to a lot of bugs in your code. So what we do is in C we use this thing called pound define, and then you give it the name of this kind of global constant you're going to do, and then you give it the value. And there's a couple subtle things here that you got to pay attention to. Number one, there's no equal sign in here. You just put the name that you're going to use for the global constant, and then you put the value. And if you just put an integer, it will interpret this constant as an integer. If you put .0 or .0 whatever, it'll interpret it as a double. Okay, so what we're going to do is let's define 3 kind of constants called R2 min, R2 max, and they'll take on values of 25 to 75. And then we'll have a number of points. And so what I mean here is that in between 25 and 75, we'll have 20 different values for R2 that will sweep from 25 to 75, okay? And then for each of those, we'll go ahead and calculate everything that we need for the current, the voltage, and the power. All right, so we are going to declare an array by typing double R2 array, and then we're going to use our global constant endpoints as the size of the array. What I've done here is I have reserved memory, and I've given it a name, R2 array, as the starting position of it, and I have endpoints worth of storage in here, and at each location it can hold a double. Okay. Now, what's cool about arrays, and you'll see why for loops are so powerful, is that when you have an array, you address each element individually by providing what we call its index. So if I wanted to access the value at this first value, I would take this thing and I would say R2 array, and then I'd do square brackets and I put 0. The indices always start at 0, and they always go up to, in this situation, it would be endpoints minus 1. And this is sweet because when you use a for loop, this is exactly what we want to do. Okay, so now here we are. We're looking at this thing, and it's like, okay, this is great. How can we do this? Well, we can have a for loop, and we can have that index variable I serve as the index for this array and go through it one by one and sit there and populate it and say, this is the value at 0, this is the value at 1, this is the value at 2, and go all the way through. And when we do it in a loop, it takes care of it automatically for us. Okay, so the loop just goes and it fills it all up. Take a look at this code right here and think about this for a second before we start typing. One of the things that I need to calculate is the step size in here. Okay, we have the minimum 25 and the maximum 75, but we don't know the step in between. And so what you got to do is you got to calculate it. Now, if you take R2 max minus R2 min and divide it by the number of points, you actually don't get the right number because you always got to remember that when you do subtraction like on your head, the subtraction is the difference between two numbers on the number line. Okay, so if you went 5 minus 2, the answer would be 3. But that means that 5 is 3 positions away from 2 on a number line. Okay, but in computers we always start at 0. All right, and so then that makes things a little bit more interesting because when we define like the range, we not only want to have the difference between 75 and 25, but we want to include 75 and 25. And so what happens is that when you try to find these step sizes, they're always going to be one less than what you originally wanted. So the way that you get around that is on the denominator, you're going to divide by endpoints, and you're actually going to do minus 1 on it. And we can test this in our code here, and I'll show you. Okay, so then what we're going to do is we're going to populate the first element in the array with 25, which is a constant, and then we're going to create this for loop, which goes from, we're going to start at index 1 all the way up to endpoints, which is 20 in this situation. Each time through the loop, we're going to increment I, and the way that this will work is we'll say at the element that I'm addressing right now, which is what I is at, so the first time through the loop I would be at 1. We're going to look at the last value by saying R2 array at I minus 1, so that means it would say I'm at element 1 and I want to look at element 0, and whatever element 0 was, I'm going to add step to it, our step, that little difference or our little step size, and then that's going to be stored into this value. And in that way, we can go doot, 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 and we can just walk through this array and we can populate it, and then we'll have the numbers that we need. Okay. All right, so let's fire this up and just see what this might look like. And the handy part of doing this is that you want to be doing print statements like continuously so that you can monitor what's happening inside of your program. Okay, so this is very close to your final recitation assignment, so I'm actually going to start up a new file called Emacs R recitation for assignment.c, and this will be kind of the final thing. Okay, so I'm going to do a pound include, and I'm going to go ahead and go standard.io.h, got my main library, and I'm going to do my pound defines. So I'm going to do a pound define, And I'm going to do R2 min, and I give it a value of 25.0. And then I do a pound define, and I'm going to do R2 max, and I'm going to give it a value of 75.0, and the point zeros are to make them floats. Then I'm going to do pound define, and I'll do n points, and let's just start off with 20. Okay, and I'm not going to put 0.0 because this will be an integer. And now we're going to do int main, don't even know what that means yet, and open a curly, close a curly, come down here, put our return 0. We still don't know what that means, but we're off and running. Okay, so the first thing that I'm going to do is I'm going to create my array. So I'm going to create double, and I'm going to name it R2 array, and it is of size n points, so that means it's going to have 20 elements in it. And now I'm going to go down and fire up a for loop. And the for loop is going to be used to populate these. So I need a few things to make the for loop work. Okay, so the first thing I need is I need my step size. So let's go ahead and go double, and I'm going to create a new double called R step. And then what I want to do is I want to say our step is going to be R2 max minus R2 min, and then divided by, and I go n points minus 1. Very important with the parentheses there, but that R step is going to be what I have there, or it's going to be my step size. Now I also need an integer I, which is my looping variable within the for loop, and I think I'm ready now, so let's test this out. I'm going to say R2 array at position 0, this is the first element, and the reason we do the first element first is because I'm going to be using it in the for loop, so I actually start at the first element, element 1, I guess it'd be the second, but I'm going to set this to equal to R2 min, and now I'm going to come into my for loop. I'm going to say for I is equal to 1. That will be where we start. We've populated element 0 in the array, and now we're going to start at element 1 and loop through the rest of them. So I'm going to do this as long as I is less than n points, and then each time through the loop I'm going to say I is equal to I plus 1. Okay, I've got my for loop all set up. I'll put my curlies there, and let's see how we can do this. I'm just going to come in and I'm going to do this. R2 array at the element that I'm looking at that is dictated by the for loop variable, which is in the first time through will be I is equal to 1, and I just put I right in the square box. Okay, so it's going to come through, and that's what's going to increment each time through the loop. And I'm going to say, I'm going to make that equal to R2 array, and I want to look at the element previous to this. So I just do it by going I minus 1, and then I take the previous value and I add to it R step. And that is now going to populate my array. Okay, now you sit there and you go, well, how do I know that it worked? Well, here's what we're going to do. We are going to create a separate for loop that will walk through each element in the array, starting at 0 this time, and we're going to go ahead and print it. Before we do that, I'm going to Control X, Control Save, and I'm going to go ahead and make sure that I can compile this. So I'm going to go ahead and do make, and this is R4A, no errors. Okay, now I'm going to do this. Watch this. I mean, you're obviously watching. For I equals 0, because this loop is my printing loop, okay? And I'm going to say I, do it as long as I is less than n points, and C is case sensitive, so you got to make sure the caps are correct. And then I'm going to do I is equal to I plus 1, and I open my curlies, and boom. Now, this will loop through, and I'm going to do the following. I'm going to say printf. And I'm going to try to do something kind of neat here. I'm actually going to print the characters R2 array, and then I'm going to put the value of I. But remember, this is the text part of the printf statement, so I'm actually just going to put my little %d, and it'll be inside of the square brackets when I print it, so it'll look kind of like it's all pro and everything. And then I'll do all pro to me. And then I'll go equals, and I'll say %f, and that's where we'll actually put the value of R2 array. And then I'm just going to do line return, okay? And now what are the variables that I'm going to put in here? Well, first of all, for the variable I want in this little %d location is the variable I, so that'll be what I see going from 0 up to 19. And then I'm going to put into this guy, the float position, the variable R2 array at the location I. And I'm legal to do that because this is how you address that variable location. Okay, so here we go. Let's go ahead and Control X, Control Save, and then I will do a make, and here we go. I'm going to run this thing. So boom, boom, and I'm going to say R4A. Oh baby, look at this. R2 array, first thing to notice is look at the I value. I went from 0 up to 19, and that worked before too. I mean, we've made a counter that did that before, but it was very powerful because we also use that to look at the actual value within this position within the array and look at how it went from 25 up to 75. While we're sitting here, let me show you what happens if you don't do this -1. So this is how you would think you would find the step size. You would just come along and go R2 max minus R2 min divided by the number of points. That's going to work great. So I come over here and I'm going to make and run, and let's see what happens. Notice that it starts at 25 again, but then it goes 25, 27.5, 30, and it goes up to 72.5. The issue is that it doesn't include, when you do the math that way, it does not include the end points. And that's how we want to define these things. And we want to say, I want the end points. When I go from 25 to 75, I want 25 to be the first, 75 to be the last. That means that there's one extra element but in the set as opposed to subtracting 75 from 25, because the way subtraction is done in the real world. The human brain defines subtraction as differences on a number line. In a computer, we want differences on a number line plus the end value, so you have to add one. So when you come along here, the way that you accommodate that, once again, is that you subtract 1 from the denominator, and that gets us back to where we can have 25 as the starting and 75 as the end. Okay, well, this is amazing because we have just now created an array to populate R2 array, and we've also created an array to print. So we are sitting here and we're like, well, this is pretty awesome. You know, I'm ready to start doing some calculations. Let's go back and look at our circuit. So here's our circuit, and we can calculate now the current, but I need to put in the program what the voltage was and what the R1 was, and once we do that, we can calculate the current. So let's take a look at that. So I'm going to come back. Here's my program. Let's come up here. Let's go ahead and just put them up here. We'll do double, and I'm going to go VS, and I'm actually going to initialize it immediately to 9.0, and I'll do double, and then I'll do R1, and let's make that 50 ohms. So 50.0, don't need the 0.0, but I now have these. And you know what I need to do is I'm going to make a new array. Okay, so I'm going to make an array which is called, iArray. Okay, so I'm going to go iArray, and I'm going to make it the same size as R2 array. Now, why did I do that? It's because I am going to calculate for each value of R2 what the value of I is. You know what's awesome about it? This right here is my populating array. So this is my populating loop. Comments are // and they turn red in here. And then this is my calc and print loop. What's cool about this calc and print loop is that I'm walking through every element in the R2 array. So I can go ahead and do this. I'm going to say I array at the index I. Okay, and this is going to start at index 0 and go all the way up to index n points -1 or 19. And I'm going to say, what is the value of I array? Well, we have to remember how to calculate it. Do you remember how to do it? It's basically the voltage source divided by the sum of these resistances. So it's V1 over R1 plus R2. So that's pretty easy to do. All I do is VS divided by, and now parentheses, I got to remember how to do this. I'm going to go R1, which was a variable, which is, I just defined it up here. So R1 is sitting up here. And then I'm going to put the value of R2. But remember, R2 is an array. So we want to go pluck out of it the value at index I. And that is how we access the array. So what's sweet about this loop is that, you know, I start at I0, so it's going to put position 0 into the R2 array, pluck that value, use it in a calculation, store it at index location 0 with an I array. Then it will loop, increment I, go to position 1 in the R2 array, calculate it, put it into position 1 within the I array, the current array, do it again, and it will walk through all the elements, and it will populate now I array with all the solutions of the current corresponding to everything in R2 array. The beauty of it is that they're in the same corresponding location with respect to their index. All right, I'm feeling pretty good here. What I'm going to do something kind of neat with this print statement. Neat to me, okay? I'm going to come along, and instead of putting the line return out here, I'm going to do a comma, and then I'm going to actually use a different print statement to print the current, because I want to see the current at each location. So now I'm going to go like this. I'm going to, let's see, what should I do here? So I'm going to go, so now I'm going to put another print statement, which is I array. Same thing. I'm going to put the index number there and then the value float, and I'm going to say I is what's going to go in the %d, and then here instead I'm going to do I array. Okay. Now in order to get my last line return, let's just do a printf and then line return, and good enough. Okay, so let's save that, and then now I'm ready to come over here and I'm going to make, ooh, error. So let's come over here, printf, where's the error at here? So R2 array blah blah. Oh, I got a little comma, dangling comma there. Let's see, I2 error expected blank before printf. Oh, my calculation up here, I didn't have a semicolon. No worries. Save that up. Boom. Come bow. Make. Run. Oh baby, look at this. So now we have our same printing, which is R2 array, and it pumped it all out to 25 to 75. For each of those corresponding resistor values, I have a corresponding current value. And look at what happens. The current starts at 120 milliamps or 0.12 amps, and it goes down, 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 down. Makes sense, because as the resistance goes up, the current goes down. And we're talking about the resistance of R2. So it's like, oh man, that was awesome. I calculated all the current, and I calculated a bunch of them. Let's go ahead and, what should we do now? How about V out? Let's calculate what V out was. Now remember, V out is the voltage across V or R2. Well, we know what R2 is. Okay, it's going to be whatever is in our array. It's a value. Okay, there's 20 of them. Well, the current is also, we have 20 current values, and we have Ohm's law. So if we know the resistance and we know the current, we multiply them together, V equals IR, and it gives us V out. So look at how easy that is to implement when I come into my program. Let's go make another array, which is going to be called V out array. And let's make it of size n points again. And check this out. I have V out array, and I'm just going to come down here and look at all I have to do. V out array at I is equal to I array at I times R2 array at I. Done. Look at how sweet this is, because I am actually populating the array, V out array, with the voltage corresponding to the value of R2 and the value of the current for that R2, and these three arrays all have corresponding indexes. So position 0 across all of them correlates to each other. So it's like, oh, this is sweet. So let's go ahead and print out our voltage. So I'm going to do, whoa, what was that? I'm going to do something cool. So I'm going to go ahead and put another print here. So I'll go V out array. And same exact thing, I'm going to put everything in there except I'll put V out array here. Let's go ahead and Control X, Control Save, and then let's make it. Let's run it. Oh, look at this, look at this. So here's V out. 3, 2, 3, 5, and it's going up and up and up and up. What's interesting about why it's going up is because it's going up because the resistance is going up, but it's not going up linearly because the current is going down at the same time. So it's kind of like creeping up, but there's kind of this interesting interplay between the current and the voltage, and it's sweet because you can really only see it when you start looking at like plots and a lot of different values of it. But okay, finally, we can now look at the power. Okay, so let's go ahead and come up here, and we'll make another array, which is a power array, and it's exactly like my I array and V out array. So I'm gonna go double, and we'll call it P2 array, and let's make it endpoints big. Okay, so now there's that. And this is great because we already have a loop that calculates the current, calculates the voltage, and power across that resistor is always just IV. So all I need to do is go P2 array, populate it at the same index as my other guys, and go ahead and say I array I multiplied by V out array I, and I'm done. So now I just come down here and let's put the print in here, and we'll go, we'll go boom. Oh, what was that? Printf. And we'll come back here and let's get this line. And I'm going to now do, I'm copying and pasting is what I'm doing on those lines there. So I'm going to do P2 array, print that out, and I want to print the I again, and I want to print P2 array, and let's take a look at what the power is going to be. So I save it, I go ahead and make it, go ahead and run it, and look at this. Here's my power. So I've got my, just a sanity check, my resistance goes from 25 to 75. My I array goes down current. My voltage is creeping up. Look at the power though. This is really fascinating. Starts at 0.36 watts, 0.37, 0.38, 38, 39, 40, and then it kind of goes up, and then look what happens. It actually starts going down. So the power is not linear. It actually has a maximum at some resistance value, and it's kind of interesting. It's like, well, how could I ever determine what the maximum power I could deliver to that resistor would be? And it turns out that it's an equation called the maximum power transfer theorem, and very easy, but you could use this program to kind of see which resistance value would lead to that. And we don't have a very fine resolution in terms of the step size, so we're jumping around by like 3 ohms. How could we change that and actually get finer precision? Well, that's the power of this global constant. What if I came in here and instead of being 20 steps, I did 100 steps, and now I come back here and I say make it, run it, and boom, look at all of this data. So I can start scrolling up and look at, I've got like a really precise step size, and you can like you can kind of see it's going up, and it kind of maxes out around somewhere in here. So what are the resistor values that correspond to that? Well, it's like, geez, they're getting pretty close to 50, it seems like. It almost looks like 50 is the value. What's interesting about it is that happens to be exactly what R1 is. Ugh, interesting. So anyway, this is cool because we have calculated all these different values. So we have done it. We've used loops to calculate something of interest. And that is it. You have done it. You have walked through all of these different flow control constructs in C, and you got yourself a big old thumbs up from me. Okay, so now what? You're done with the video. You're going to take the Recitation 4 quiz. Go to your recitation and work on your program. Keep in mind, the program is different from what I've gone through, but if you were working along, you're going to have the vast majority of the code. It's just going to be some slight tweaks to make sure that you actually typed it in and know how to incorporate a few things from past recitations. And then after you've demoed it, there's going to be a question with your demo in terms of just some observations you've made about the results you're going to get. And then you upload your program file to the Recitation 4 code upload assignment folder, and that is it. Good luck.